Hey everybody. So I saw a lot of people really kind of struggling with the first couple of questions in the lab, and it occurred to me that I really hadn't explained, how to build a data set to represent a function, right? I guess that seemed simple to me, and so it didn't occur to me that it wouldn't be simple to people who were just starting out. So I'd like to go over that for a little bit, and I'd like to show you some of the solutions to the questions 3, 4, and 5, basically, from the lab, just to make sure that we're all good on that. So, and I don't have a presentation for this one. I will post the code I'm about to write, though. So if we have, well, let's actually not get ahead of ourselves too much, right? So the first couple of things that I trained were neural networks that learned a binary rule like XOR, right? And if you think about this, this is really defined at 4 points, right? So each one of these binary values or variables can have one of 2 sort of Boolean values, 0 or 1, right? And the output can also only have one value. So neural networks are real valued, though. So what we're actually using is, 0.0 and 1.0. And because tan h is, or because 1 is sort of at the edge of tan h's range, right? So tan h looks like this. And I know I've drawn this several times, right? But again, just so we're clear, it approaches the value 1 at infinity, right? So an output of 1 is going to pull the input of tan h. It's going to want to have our tan h activation approach infinity, which means it's going to cause our weights to explode, and that's bad. So we usually replace this with 0.75 because that lands more in the linear bit, right? And I know I've explained this several times, right? But this is how we sort of constructed our sort of logical function. And this is simple enough that we can just use, let me write that a little bit smaller, right? And let me change the pen color. So this is simple enough that we can, when we're building this data set, just directly enumerate every value that this could have, right? Because there's only 4 of them. So if x is our input, we need an np.array. You know what? I'm going to have to rewrite this because it's just too small. Sorry, everyone. I'll be quick about it. Yeah, that's correct. All right. So there are few enough of these that we can just directly enumerate them, right? And we can pack them. Right? So there is our column vector, right? That looks like this, if you can't read it very well because it's on the edge of the screen. Column vector of our input, right? That represents the pair A, B, right? And then I had like a function down here, right? That was like if A and not B, and it would generate the D, depending on that. So a question that a lot of people had looking at this code was, what do you do for example, the function in the plane? Well, okay, so before I skip ahead to that, a question that a few people had was, all right, so how do you modify this for example, the AND rule, right? So one of the first questions that you should ask, given to you in the lab is a network, right? that maps 2 inputs to 3 outputs with a hidden layer, right? And one of the first questions you should ask is, do we have to change the architecture of this network? And you don't, right? So if you already know how to learn the XOR rule and you want to learn the AND rule, you can reuse this, right? Because XOR is 2 inputs, 1 output, and AND is 2 inputs, 1 output. So for the first problem, and I think the second one, right? Because I think the second one is not XOR, right? Where not XOR is this, right? So for the second problem, the first and second problem, you can just keep the network unmodified. All of the forward and backpass stuff does not have to change. All you have to do is change the dataset generation. You don't even have to change this part, right? The part that's just enumerating the 4 combinations of Boolean values. You can keep this. All you would have to do is change the thing that generates the D, the label, the desired behavior, the model output, right? Not model output, but the label or desired behavior, right? All you'd have to do is change D. So the third question asks, excuse me, for you to train a function that learns to have constant output of 0, right? I did not say this explicitly, and maybe I should have, but kind of the intent was to use the same network, right? So our network that maps 2 inputs to 1 output, we can once again keep this thing, right? We can train this architecture to have 0 output regardless of what the input is for a certain range, okay? And so now we need to think about what our data set should look like for this. One student suggested that we just have 1 element in it, right? Something like, well, let me write it in the style of a column vector, right? Something like this. Right? Which is, which is the 0.5, 0.5 in like matrix notation, or if we were going to write it in NumPy notation, this, right? A sort of 2D column vector. And then just specify an output of 0 at that point. So the problem is that actually isn't going to work. All right? Not a bad idea, it's not going to work. And a game that I kind of played with the students in the Thursday group is, imagine you're my neural net, and alright, sorry, edit point, because I messed something up. But, yeah. Imagine you are my neural net, right? You are my neural net. Okay? And I'm going to tell you that. So we can think of our 2 inputs, right? Our 2 inputs are real values, and we can think of them as encompassing a 2D plane, right? You are my neural net, and you have 1 output, right? So 2 real valued inputs, which we can interpret as points on this real plane, and 1 output, which we can interpret as a point somewhere on the z-axis, right? A height at that point. So if you're my neural net, let's say I tell you that at a certain point, say 0.5, 0.5, I want you to have a value, I'm going to say of 1, okay? So we're going to skip a little bit ahead to the constant output one. And I say I want to have a value of 1 there, all right? Now, I train you heavily on this 1 point, and then I ask you, so at 0.75, 0.1, whoops, what output are you going to produce? Think about this question for a minute. So, one student guessed, maybe you're going to output 0.85. And the reasoning was, this this, right, is this plus this. If you're a human, that's not a terrible guess. But if you're this little bitty neural net, you probably don't have that kind of intuition, right? If you don't have human intuition to fall back on, and you're just this very simple mathematical model, what do you do, right? Neural nets kind of pick up on patterns and regularities in large amounts of data, and if I just give you this one input-output pair, you don't have enough data to abstract the pattern from. If you're my neural net and I want you to pick up that the pattern is 1.0 everywhere, then I have to kind of give you samples from everywhere, right? I have to say, and then it's 1 here. Oops. And then it's 1 down here, and it's 1 everywhere, right? So what I basically need to do is I need to generate a lot of data that covers this sort of 2D plane, right, and is 1 everywhere. So what I want to do is generate that kind of input. And there are a couple of ways that we can do that, all right? So one way is I could make a regular grid that covers the whole input space. And I'm going to use a different color for the grid just so it's a little bit easier to figure out what is axis and what is grid, right? So I could generate points at regular intervals, and you could do this with like a double for loop, right? I miscounted that column, but who cares? I could generate points at regular intervals and specify a value of 1 at every one of those. Also, though, and this might actually turn out to be a little bit easier, I can just generate a whole bunch of points at random. If I decide that I want 1,000 points across this plane, it's actually pretty easy to just generate 1,000 random sort of pin drops, if you will. And if I generate a large number of points, I'm still likely to cover the plane pretty well, right? So in this scheme, we might have... Is that the orange one? Nope, that's not orange. That's not orange. This is the orange. So in this scheme, we might have a double for, right? And I'm going to kind of pseudocode this, right? So it's something like 4x1 in 0 to 1, right? And then 4x2, and this is obviously not real Python code, in 0 to 2, because we're going to see that in a minute, right? Oops. And cover the plane in a grid this way. Over here, I might just do 4i in, some large number. X equals a random point, right? And that way I'm just kind of pin dropping at random everywhere. So let us actually look at that code. Here is code that accomplishes the constant output problem. So most of this is unchanged except right here. Here, well, okay, another thing that I actually should say, that I meant to do, several other people asked, what does the data set even look like? So before I jump to that, let me specify what the data set looks like, right? So the data set is a list of input-output pairs, right? So if I want 200 points in the plane, I need 200 pairs of an input point, right? And the desired label at that point as numpy arrays, right? Where x is going to look like this. And then the output label, the desired behavior, is going to look like this, right? Or 1 or 0, depending on which problem we're doing. Yes? And so this is sort of equivalent to, right, the geometric point x1, x2. right? Yes. And then I've got a list of these. And here I'm writing them as tuples. I believe in some of the code I've used lists. It actually doesn't really matter, right? One of the major differences is that tuples are immutable and lists are not. Since we never try to mutate these, that doesn't really matter, right? So this is what our data set is going to end up looking like, right? A bunch of x's where we're going to interpret these column vectors as points, and then a bunch of outputs that are just a constant value everywhere. All right, so with that said, let's look at the code, okay? So here, I am just sort of randomly sampling all over the plane. 200 times, I am going to get an x that is a random point where each component is in the range 0 to 1. So again, we're picking the sort of positive real plane, right? Somewhere in here. And of shape 2, 1, right? So it's going to be shaped like this. Right, where this is a 2D array of 2 random values, and I hope we can see how that is equivalent to a random point dropped somewhere in this 2D plane. Okay? Then, I'm creating my output, and since this is constant, my output is always 0.75, and I'm storing a tuple of those two things in my data set. Okay? So this, basically, is the complete solution to problem 4, right? Or I should say that's all you have to change for problem 4. The rest of the file you can leave unmodified. And I've commented out this thing. A couple of people wanted to know what that was. There's a couple of different ways you can inspect what your network is doing. We can use the loss. There are some cases, so if our loss goes down, right, that's usually a good sign. There are some cases where the loss can be small even though your network is not doing well, which is why I also have it down here print out its output directly. This is not one of those cases. This problem is very simple, and if our loss goes down to a very small number, we're probably doing very well. All right. So I've commented out this thing that was just printing the output at every sample, and I'm going to use this thing that just plots the loss with matplotlib. So I don't think I changed the rest of this, right? The rest of this code is more or less as it was in class. We're going to use this data set that gets 200 random points, and we're going to just print, or so we're going to plot our loss. So let's run that. Boom, and there we go. Unsurprisingly, this problem is fairly simple, and our 2D or 2-layer network can learn to accomplish this pretty well. Our loss starts out high because our weights are random, but oops, then very, very quickly it becomes very small. Excuse me. So, as you can guess from these titles, I also have the regular grid. Here, I use a double for loop. So for values from 1 to 100, I divide them by 100, which means that I'm counting from 0 to 1, right? 0 to 100 divided by 100 is 0 to 1, right? And then I'm doing that again. x2 is 1 or 0 to 100 divided by 100, right? Then I am packing both of those, so x1, x2, I'm packing both of those in a NumPy array, right? And then I am once again creating my constant output as before, and once again packing a tuple of those things into this list, right? That is my data set, this list of input, output tuples. And if we run that, oops, forgot I had that code in there. we see, once again, I'll come back to that in a second, we see once again that our loss starts out at some moderate random value, starts out at some moderate value because the weights are random, zoop, really rapidly converges. Finally, that's the same thing we had before. All right, yeah, so good. So we won't have to talk about that because it's the same thing I had before. So I guess I will go ahead and mention this. This is a trick that I was going to mention at some point. I suppose now is that point. I wanted you to be able to see what your loss is doing while it trains. To make that work, I imported sys, which is the system module. I then used sys.stdout, which writes to the same thing that print writes to. It just writes to it as a file stream. So I first write the message training, and I have to include a trailing new line because stdout.write does not do that, right? It doesn't work like print. Print advances the line for you, stdout.write does not. This, ignore this little carriage, or this sequence right here. This, whoopsie, prints I, which is the update, right? And the current loss. So right now, just focus on the fact that it's printing I and the loss. And it's doing this every 250 updates. So this, the control R, is a carriage return. That returns the print position from wherever it is back to the start of the line. Therefore, whatever we write is going to overwrite whatever was already on the line. So what that means is, every 250 updates, I'm going to rewind the print head and then print a new message with the current update count and loss. Okay? That is why, if you look at it, right, you see this number going up and then this number going down, right? It's because the old message that was here keeps getting erased with the new one, right? Then at the end, I have this print command with a line feed that finally advances the line and it prints the time. So this thing, the :8 and the :9.4e, those are format specifiers. That's what is causing this to always be the same length, right? That :8 means to print this 8 spaces. The :9.4e means to reserve, I should say, 9 spaces for this, to use 4 digits after the decimal always, and to always use exponential notation. So those are formatting commands that make this print in such a way that its size on the line is fairly consistent. So the other thing I wanted to do is time it, and that's what this is doing. And timing this is really simple. I import the time module. I get the start time. Time.time just returns a double. And I forget what that double is. I think it might be seconds since the epoch in milliseconds. I think it's seconds since the epoch. Is the epoch 1997? I've forgotten what the epoch is. But it's seconds since the epoch. And in with millisecond precision as a double, right? And if that's complicated to think about, don't worry about it. The only thing you need to understand is that this gets our time in seconds since, like, start, right? So start is some number that is the time since some special point, seconds since some special point. Time.time is another number that is seconds since some special point, and the difference between them is the difference between these two calls, right? So I'm timing it, and I'm taking 8 seconds to train. Okay. So another question asks you to modify this thing to do a function. For that, if our function is still to input to one output. And if our function is reasonably simple, right, we can keep using our 2-3-2-1 network, right? So when I say reasonably simple, there are computable functions that map 2 input to 1 output that would completely befuddle and confuse this network, right? That are non-simple. Hopefully, and I will admit, I didn't try it beforehand, the function that I asked you to model is sufficiently simple. So to do that, again, we're not changing our network. I didn't say to well, actually, what did I say? I forget if I gave you a specific range it had to be. 0, 1. Okay, yeah. So good. I said to use 0, 1, so we can keep our iteration over that grid of points the same, right? We still have a 2D grid, and we still have a grid covering the 2D plane, and we can reuse that code. So all we really need for this problem is to change the code that generates the label, right? So here, I'm going to compute the function. The assignment says x1 plus x2. That's a typo on my part. It's supposed to be times, right? But if you wanted to do that, and if you wanted to think about this in terms of times instead, you could just, or if you wanted to think about this in terms of plus instead, you could just do that. So, quick question. Think about why plus was an error, but times will work. Think for a second about that. Hint, remember what that graph of tan h, if I could draw, remember what that graph of tan h looked like, right? But, yeah. So I am going, so here I just compute 3 over 4. If I wanted to be really optimal, I would just cache this, right? This thing I told you to multiply it by. Then x1 times x2. And then I just put that as my output at a point in this nd array, right? So I'm still generating a bunch of x1s and x2s. I'm still wrapping those in my x numpy array. And then I'm producing n, which is x1 times x2, putting that in my numpy array and storing it. I'm not changing any of the iterating over points code. I'm not changing any of the neural net code, right? All of that can stay the same. And if we run this, our loss is small, although it may not be as small as we might have thought it was going to be, right? Again, this is a little bit noisier than we might have wanted it to be. I think there is a reason for that. If you think about what this looks like, it looks something like this. For small x1 and x2, the product of those two things is small, and then it's only going to approach 1 in the extreme, right, of each of these. So it's this kind of shallow depression that becomes steep only out here, right? See that? And I think the fact that it's only really going to approach 1 on this corner, right? Oh, actually, no, I just realized I misdrew that. Because it's actually 0 for this entire thing, right? Because this is 0, right? So it's 0 along each of these axes. So even out here, it's 0 times 1, 0. So it's actually going to be doing this. There we go. Sorry about that. Sorry for the confusion. It's actually doing this. And our 2-layer sort of four width network just kind of might really struggle to capture a thing that is so flat most of its area and then just kind of shoots up in the corner, right? So if that is the problem, what could we do? Well, we could make our layers wider, and we could add more. Homework doesn't ask you to do that. If you feel so inclined and motivated, you could try to find a configuration for this network that is going to approach a really teeny tiny loss rapidly, right? I'm sorry, it's going to find I said loss. Find a network that will approximate this function to a much smaller error. Although it might just help if I train it some more. So let's try giving it 3 times the training and see what we do, shan't we? So some of the later questions ask you to change the network to make to add a layer. I know one of them does. I'm not going to go much into how to do that. And because I think that should be fairly self-explanatory given all of the matrix operations I had you practice last week. That's why, right? Oh, there we go. All right. Yeah, so if we just train it longer, we have an initial sharp decrease, some noisiness, and then it finally does approach arbitrarily good precision. All right, cool. But yeah, I think the thing where it asks you to add a layer should be fairly self-explanatory. You basically can just copy this to make W3 and B3, and then you can just kind of repeat that code down here to expand the forward pass, and then down here to expand the back pass. And ideally, right, you should be able to, if you've understood everything in the videos, you should be able to do that without too much headache. And the only slightly tricky part is going to be making these dimensions add up, okay? At each layer, this needs to be the number of inputs to the layer, this needs to be the number of outputs to the layer, and this needs to be the number of outputs to the layer, okay? And these two need to agree. The inputs to the next layer need to be the outputs of the previous layer, right? So this number here and this number here have to agree, because layer 2 has to have the same number of inputs as layer 1 had outputs, right? So if you know all of that, then you should be good to do those without too much issue. Let me know if that's the case.